And then just begin in your own time. Okay.
My name is Ludger Wirtz. I'm a professor for theoretical solid-state physics at the University of Luxembourg. So in solid-state physics, we try to understand the macroscopic properties of materials from the atomic structure. That means from how the atoms are arranged in a solid. And with that knowledge, we can calculate different properties such as the color, the hardness, electrical conductivity, and so on. So in my presentation at this conference, I talked about how two-dimensional materials interact with light. And this knowledge is very important because, first of all, we would like to know the color of those materials. We would like to know how they absorb the light. And then we would like to explore their utility in photosensors and in solar cells, just to give two examples. In parallel to practical applications, there are some interesting fundamental questions. In particular, it's interesting to investigate with the laws of quantum mechanics what is going on during the excitation with light, during the process that a photon, an incoming light particle, is absorbed, and that electrons are excited from what we call the valence band to the conduction band. There is some complicated physical mechanism behind, some equations that I will not elaborate here. But roughly, when you excite an electron, a negative charge, then a positive charge remains in the valence band. So the positive hole and the negative electron interact through a Coulomb force, like the electron and the proton in the hydrogen atom, and this leads to bound states in the forbidden band, and those states are called excitons. And they form a series of excited states in a way very similar to excited states in the hydrogen atom. And this is known from many three-dimensional materials, but it is particularly pronounced in two-dimensional materials, where we see strong signatures of excitonic features in the absorption spectra. Now, in future activities, we are investigating the time-dependent process, so how light is exactly absorbed and how the excited state occupation develops in time. Important for this is the calculation of the lattice vibrations, because often we assume that atoms are standing still, but in reality they are always in movement, they are always oscillating around their equilibrium position, and this influences spectra in a very important way. A particular challenge is to calculate how materials react to ever shorter light pulses, meaning ever more energetic light pulses. So eventually pulses that are so intense as to pulverize the material, leading not only to electron and photon emission, but also to an emission of ions from the material. And yet another challenge is to automatize our calculations, such as to calculate a large number of materials in an automatic way and to build a database of many spectra in an automatic way. So there are still many questions for the coming years to go, and I'm looking forward to the next conference in 2 years from now on.
Thank you. That was